Okay, the first video of this section was all talking about conceptual things, increasing, decreasing, positive derivative, negative derivative, and its connection to the first derivative test, where if we have a critical point and we go up and then down, and it's continuous, that's a local max. And similarly for local mins, this video is just going to get some practice using this and connecting some concepts with 4.3 as well. Example 1, our very first example. Find and classify. Find and classify the local extrema for the following functions. Part A is going to be the function y equals x cubed minus 3x squared minus 9x minus 1. We'll do this by hand and we'll graph it and we'll say, hopefully this is right. So let's do it. So remember, to find local extrema, they have to occur at critical points. So we're going to find all the critical points. And in the past, we graphed it to do it. But now once we find the critical points, we're going to use the first derivative test to classify them by hand. All right, so that's going to be our first step, is find the critical points. And again, remember, critical points are when the derivative equals 0 or it's undefined. So we'll calculate the derivative. My cats are really racing around today. 3x squared minus 6x minus 9. Well, this is defined everywhere. This is a quadratic. This is a parabola. So it's never going to be undefined, but it will equal 0. When does the derivative equal 0? Well, when this is true. And now we have to solve this. Now you could use the AC method here. You could use the guess and check method. But if there's ever a greatest common factor, the least common factor is 1. Very useless thing, the least common factor. If there's ever a greatest common factor, we take it out and it makes our factoring a lot easier. Could also use the quadratic formula. Here we go. And now we need two numbers that multiply to -3. That add to -2, and I believe these work. So we're going to say that we have a critical point when x is equal to 3 and when x is equal to -1. Now these are not the critical points. These are the locations of the critical points because critical points are points. We would have to plug these in to get the y values. So it's going to do that. Critical points at the point 3 comma something and -1 comma something. And remember, we have two functions. Which function are we using? Well, we want the y value. So we plug it into the original function. Original function gives the y value, the height. Derivative is the slope function. It gives us the slope. And specifically, we know if we plugged it into the slope function, we should get a slope of 0. So if we plug it into this one, plug in 3, we're going to get 27 minus 27 is 0. Minus 27 minus 1 is minus 28, I believe. And if we plug it in, if we plug -1 in, we're going to get -1 minus 3 is -4. Plus 9 is 5. Minus 1 is 4. Should probably use a calculator and not try to do these in your head, but that's our first step. We'll check those answers later and find whether I did it right. Okay, so these are the only options for local extrema. So then, all that's left is classifying them with the first derivative test. So let's look at this first point. At the point 3 comma -28. How does the derivative work? And the way that a lot of times we use the first derivative test is we make a little number line. And we look at these x coordinates, 3 and -1. This is going to be our step 2. First derivative test. So let's say 3 is over here and -1 is over here. Doesn't matter how nice your number line is. Well, let's just look at what is the sign of f prime in each interval. Because this is continuous, the intermediate value theorem says that if it's 0 here, the only place it can change is when it's crossing 0. So the only place the sign can change is at these points. So if we find the sign of the derivative here, that means the derivative has to be that same sign in this entire interval. Intermediate value theorem. Since the derivative is continuous, the only time it can change signs is when it's 0, which is right here and right here. Okay, so we're just going to look at some signs. So look at something in this interval. We want to know what is the sign of the derivative in this interval. We only have to look at a single point. And then everywhere in that interval will have the same sign of the derivative. So we can look at maybe pick some number, any number, f prime of any number in that interval. -2, -5, -1 billion. That'll tell you the sign of the derivative right there. I'll use -2. Well, the derivative at -2 is going to be, you can plug it into this, or you can plug it into that. Since we're only looking at the sign, the factored form is often more useful. 3 times x minus 3. Let me write that down again. 3 times x minus 3 times x plus 1. So when we plug in -2, we get this, and we don't even need to plug it into a calculator. All we need to know is look at the sign. Right? This is a positive times a negative times a negative. What does that equal? That equals a positive. So in this entire interval, everywhere to the left of -1, the function is increasing. So yeah, on the top, let's talk about the sign of f prime, and on the bottom, let's talk about whether it's increasing or decreasing. So it's increasing. Everywhere to the left of -1, it's increasing on that entire interval. Well, now we can pick something in the middle. You could pick 0, you could pick 1, you could pick E, Euler's number, 2.718. Pick anything in this interval next. I like to pick 0. 0 is a great number. It's going to be 3 times 0 minus 3 times 0 plus 1. What's a positive number? Times a negative number times a positive number. That's a negative. So everywhere in the middle, the derivative is negative. Everywhere in the middle, the function is decreasing. And that immediately tells us whether -1 is a local max or a local min. But we're going to wait on that. Let's fill in this chart. This chart is usually the most useful way of visually looking at the first derivative test. Okay, but we'll circle back to the first derivative test and really make sure and connect why this chart is useful. So pick something in this last interval. Could be 4, could be 5, could be 3.2, could be pi, could be a billion. Pick something in that interval. I'll pick something easy like 4. And that's going to give us this. And again, you don't actually have to plug this in. Just look at, well, this is a positive times a positive times a positive. That's going to be a positive. It's increasing everywhere on this interval from 3 to infinity. The function is increasing. So that gives us all the information that we need. Okay? And that's how we'll express our answer. Increasing to decreasing at -1 means local max. Up and then down is max. We're going to say there's a local max of, at -1, the function value is 4. When we say local max, it's always the y value. Local max of 4 at x equals -1. And similarly, a local min of -28 at x equals 3. Again, assuming I plugged in my y values correctly. Let's check our answers. Let's check my work. And let's visually connect this information with Desmos. Where are you, Desmos? You're not Desmos. Let's graph the original function. Y equals x cubed minus 3x squared minus 9x minus 1. Local max at -1, comma 4. Great. That's what we had. Local min, pretty far down, at 3, comma -28. That is indeed a local min. We also said, let me zoom out on the y's without zooming out on the x's. We also said, look at this chart on the top. We said everywhere to the left on the interval from on the interval from negative infinity up to -1, the function's increasing. The function, as we go left to right, the function is increasing. It's going up all the way up to when x is -1. But as soon as x is -1, the function's not going up anymore, right? Function's now going down. We said, look at that middle interval. The derivative is negative here. Everywhere from -1 to 3, the derivative is negative, so the function has to be going down. And indeed, when x is -1, the function starts going down. The derivative is negative. The slope is negative all the way until when x is 3. And then again, after that, we said after 3, when to the right of 3, from 3 to infinity, the slope once again becomes positive. And you can see that this function again goes up for the rest of that interval. So that is really connecting all of this stuff that we've been talking about. And notice that we did indeed use the first derivative test, but we didn't really prove it. Like if we were really trying to prove it, we should have commented this function is continuous for all real numbers. So of course it's continuous on some interval that has our critical points. We could also comment on how the function's differentiable on the entire interval. And then use this information as well. I'm going to be a little relaxed about this. If we were doing formal proofs, that's what I would expect from you. But here, I just want you to be able to find it and show your work. So you should be showing the work that I'm writing down, but you do not have to write a more formal proof on this. Yeah, this is indeed what we did. We found our critical points, and then at that first one, right, it was going from positive to negative. That's why we said it was a local max. Second one went from negative to positive, and that's why you said it was a local minimum. So I'm going to write down one more problem. I would highly recommend that you pause the video right now and try to do this next problem on your own. Pause it, work on it, and then compare your answer and your process with my answer and my process. Okay, so we're going to approach this the same exact way. We're going to start by finding the critical points when the derivative equals 0 or is undefined. To answer questions about the derivative, we need to take the derivative. Using the power rule, we're going to get the 1/3 coming down, subtract 1 from the exponent. It's now -2/3. The 5/3 comes down, subtract 1 from the exponent. We now have 2/3. And it could be useful. Both forms are appropriate, but it might be useful to write this in a different form. This is 5 divided by 3 times the cubed root of x squared minus 5 times the cubed root of x squared over 3. And if you're not sure which form you want, write them both. All right, and then you have both of them accessible whenever you need. Remember, for rational exponents that are fractions like this, the negative exponent means it goes to the denominator. The numerator of the exponent is the power, and the denominator of the exponent is the index of the radical. So we need to find when this is equal to 0 and when this is undefined. We'll start with the easier one, I think. Right, it's undefined when x is equal to 0. That's the only way that can cause this to be undefined. It's undefined when we divide by 0. Most frequently is that's what we're going to see. So we're going to have a critical point at 0 comma something. Let's just do it right now, right? If we plug in 0 here, should get 0 comma 0. You could use a calculator to plug that in as well. Well, we also have to find when is the derivative equal to 0. We're going to have to solve, oops, I forgot to switch colors. We're going to have to solve this equation. The last equation was a nice quadratic equation. This equation is a little bit more complicated. Remember that whenever you have an equation that you're solving for that has fractions, one of the best techniques, one of the best ways to start is to multiply both sides of the equation by the least common denominator. In this case, the least common denominator is 3 times the cubed root of x squared. 3 times the cubed root of x squared. Now the left-hand side is great. Multiplying something by 0, well, it's still 0. The right-hand side, we are going to have to distribute. In the first product, they just cancel. We're only left with a 5. In the second product, the 3 cancels. We have the 5 cubed root of x squared from before, and we're multiplying by another cubed root of x squared. So in this case, once we're here, I think this kind of format's a little better because when you're multiplying things, you can add the exponents. But you can keep it in both forms, depending on what you prefer. So either way, this simplifies to the cubed root. As long as the square roots, they're not square roots, as long as the radicals have the same index, you can just multiply their insides together. And we'll get x squared times x squared is x to the 4th. Let's keep solving this. We can add that radical over to both sides, get all the variables on one side, get everything else on the other side, divide both sides by 5. Divide both sides by 5. We can cube both sides now. That's going to give us x to the 4th is equal to 1. And now take the 4th root of both sides, and because it is even, we're going to get plus or minus the 4th root of 1. We're going to get plus or minus 1. There's a lot of somewhat strange algebra in here, so it can be a good idea to go back and check our answer. If we plug in positive 1 or negative 1 here, do we indeed get a derivative of 0? And you will. It also should make sense looking at this derivative function. I wish I erased this thing up here. It should make sense looking at this derivative function that our answer should be both the positive version and the negative version. Why? Because everything in this function has a squared in it, right? This whole function, every variable, right? Everywhere that x appears has squared. So anything that happens at once, one side of x should also happen at the other side of x. This is what's known as an even function. We'll see that graphically when we check our answers at the end. So critical point at 0, 0, at 1, something, and at negative 1, sorry, the derivative is an even function. The original function is not an even function. Sorry. The original function is not even. So we plug in 1 here. We're going to get 5 minus 1. Again, I suggest you use a calculator. But to save time, I will not be using a calculator. 5 minus 1 is indeed 4. When we plug in negative 1, we're going to get negative 5 plus 1, negative 4. I do believe this is an odd function. Yes, this is indeed an odd function. We can see that graphically. The original function is odd. The derivative is even. Remember, that has to do with symmetry about the origin and symmetry about the y-axis, respectively. So these are our 3 critical points. That's the first step. Second step is use the first derivative test on these critical points. So just like before, we're going to make a little number line. I'm going to say, let's say -1 is here, and then 0, and then +1. Again, these are just the x coordinates of the critical points. These are the locations of the critical points. Now we're going to look at, well, what is the sign of f prime on each of these intervals? And then also, is it increasing or decreasing on each of these intervals? Technically, this is not a continuous function anymore. But each of these intervals, it's continuous on each of these intervals. It's only discontinuous. Actually, no, it is a continuous function. It's just the derivative that's not continuous. Anyway, let's plug in some values and get some results. So again, it can be useful. I should really be consistent with my colors to make things a little bit more manageable. It'll be useful, again, to remember what our derivative is, because we're looking at what is the sign of the derivative at different places. The derivative is 5/3, or 5/3, cubed root of x squared, minus 5 cubed root of x squared over 3. So we just want to look at the sign of the derivative at every point, or at some point in an interval. So let's start by picking any point in this interval. Any point to the left of -1. I'm going to choose -2 because that's an easy point. That's going to be 5/3 times the cubed root of -2 squared, which is +4, minus 5 times the cubed root of -2 squared, which is +4 over 3. I'm going to use a calculator for that one. I'm not going to do this one in my head. Again, if f of x is equal to 5 divided by 3 times the cubed root of x squared, you can type in cubed roots as exponent of 1/3 like this, minus 5 times x squared, the cubed root of that, all over 3. That is our derivative. The derivative at -2 is negative. The value doesn't matter, only the sign. So that is going to be negative. So the derivative is negative to the left. It's decreasing on this interval. And again, the original function is continuous, so we're good to go. Now we pick a point on this interval. Can't pick -1, can't pick 0. Have to pick something on the inside of the interval. We'll do a half. And again, I'm going to use a calculator on this one as well. At 1/2, it's positive. So it's positive everywhere here. We know that that first location, -1, is the location of a local minimum. So let's keep going. Pick a point in this interval. Oh, I made a mistake. Positive. Oops. I plugged in positive 1/2, right? That's this interval. Let's plug in -1/2 to get that other interval that I missed. It is also positive. All right. Sorry, we're plugging these into the derivative, rather. Sorry. It's an even function, remember? Even function means it should be the same to the left as it is from the right. The derivative is even, the original function is odd. So that's telling us that 0 is neither a local min nor a local max, because it's increasing on both sides. And finally, we could do the same thing for the last one. We should get a negative value for the derivative at +2. Let's just double check it just to be safe. And indeed, it is a negative value. So Using the first derivative test, we can make some conclusions. We're going to say there's a local min right here at -1. So the local min of -4 at x equals -1. There's a local max. Goes from positive to negative, and the function's continuous. Derivative is not continuous, but the original function is continuous. Goes from positive to negative on this interval. We have a local max at x equals -1. The local max is 4, and it occurs at x equals +1. That's our answer. Those are all the local extrema. There is a critical point here, but it's not a local extrema. Not a local extremum. Let's plot the original function and the derivative on the same axes and see what we got. This is 5x to the 1/3. I thought this was going to be a short video, but I'm trying to give a lot of context on these problems. All right, we have the original function. Oh, it was hidden. Original function, ooh, looks pretty wacky. Looks really wacky, huh? We have the original function and its derivative. So we said there's a local min at -1. Ah, great. We said there was a local max at +1. Ah, great. We said there was a critical point at x equals 0, but it's not a local min or a local max. So remember, local max, the biggest around, the top of a mountain. Local min, the smallest nearby, the bottom of a valley. And we do indeed see those here. And then again, let's just, we checked our answer, we're done. But I just want to connect some concepts between the original blue graph and its derivative red. Orange, rather. Orange shows the slope. Notice that everywhere to the left of -1, the value of the slope function, orange is the slope function. Everywhere to the left of -1, the value of the slope function, all of these function values, are negative. That means that everywhere to the left of -1 on the blue graph has a negative slope. It's decreasing. Negative slope means decreasing. The blue graph is indeed going down on that interval. And then between -1 and 0, the slope is positive. The slope function, the orange graph, tells us the slope of the blue graph. The slope function has positive values, and specifically, the slope function on this interval has positive values. They get really, really big. Well, yeah, to the right here, to the right of here, the slope is positive. The blue graph is increasing. It's going up. And it starts getting really, really steep. It gets vertical. The slope becomes infinite. And then it starts, well, and then it still is increasing. And you can keep on going. And again, just like I promised, the original function, the blue graph, is an odd function. Odd means it's symmetric about the origin. Any x comma y will also have a -x, -y. And I said that the derivative function was even, which means it's symmetric about the y-axis. Symmetric to the left and the right of that y-axis. And again, that one's a more easy reflection to see that, yes, we have that symmetry, kind of like my face, but not like my glasses, which are a little crooked. I hope that doesn't bother you forever, knowing that my glasses are crooked. It's like one of those things that you don't think about, and then someone says something, and then you can't stop thinking about it. Sounds are like that for me. So that's the end of the video. That's the first derivative test. That's how you use the first derivative test. In the next video, we're going to start talking about second derivatives, a concept called concavity, points of inflection, and we'll use that eventually in the fourth video to come up with a new test. All right. Have a good day. Bye-bye, and good luck.